Okay, you go back to your calculating temperature using stars in the spectroscope. There's the solutions to your spectroscope, but that's my take on it. Yours probably is not as detailed and is more concise. I've tried to make sure that I've added as much detail as possible. So please make sure that you do look at the solutions to this and flesh that out. And then when you are putting it into your yellow book, then make sure that you have, because that one there asks you to draw the diagram and annotate around it. So you create a story with your picture. Now, yesterday we were together, we were having a look at what was going on when we were looking at a spectra through a spectroscope of a light globe that was getting hotter. And it asks you to have a look at what would happen as you increase the temperature. If you have a low brightness, firstly the colour is a dull orange, then it became yellow, then yellow-white. Those were the colours that we decided. And as the globe got hotter, it got brighter. Okay? So that's the first thing that we notice about it. And then what are the types of spectrums and so on that are present? Low brightness, once again it's a dull orange, all the colours are present, but if you actually could really determine it, if you really looked at a very long time, you should have noticed that the red colours were much richer, much more present. Is that making sense? When you went to medium brightness, and it was a bit of a yellow, you wouldn't have noticed it. You would just see an entire spectrum and you wouldn't have been able to work out which parts of that spectrum were brighter or so on. But in reality, the centre of the spectrum is much brighter. That's the ones in the green and the yellow. And the high brightness, once again, you should have seen that the blue and the violet became a little bit more pronounced this time. Though you really, once again, your eye is not a very good measure of all this. What I did not get on to yesterday was the different types of spectrums. And there are three, so let's go back to those ones now. When we have a look at spectra, we actually can determine that there are three different forms of it. The one that we are most familiar with, because when we look up into the sky we see it, is the continuous. So the first one up here is a continuous spectrum. Now the continuous spectrum is a rainbow which it's continuous. It doesn't have any dashes or black lines or any thing which is different to it. The second, so that's continuous there, is what we call, some people call it the dark line spectrum. It's a continuous spectrum in its background, but it has dark lines over top of it, and its proper name is the absorption spectrum. And I can never, have I got that right? The absorption spectrum. Okay? And you'll understand why it's called an absorption spectrum very soon. The last, also called the bright line spectrum, is the exact opposite of the absorption spectrum. Whereas the absorption spectrum is continuous with black lines on it, the last spectrum, the bright line, is the missing lines from up here are on this. Okay? So this is a black background with coloured lines on it, and it is called an emission spectrum. Okay? Now, those three are the way a photograph would see them. Okay? So if you were to take a photograph of a continuous spectrum, it looks like that. An absorption spectrum, it looks like that. an emission spectrum, it looks like that. Now, the one thing that we need to realise is that our eyes are really bad at determining the depth and richness of colour. So all of these have to be run through a computer to get what we call a radiation intensity curve. Now, a radiation intensity curve looks like this, and we were doing it with it yesterday. Whoops. And now, yesterday I used an applet which showed you a radiation intensity curve, and a radiation intensity curve looks like that, where it takes the spectrum, and here's the spectrum, I'll put the spectrum above, just a little bit, which is the visual spectrum, and we'll say this is the red, this is the orange, yellow, green, cyan, blue, violet. Okay? So this little section here represents the visual spectrum. This part here is the radio end. Now the radio end contains what? Radio, microwave and infrared. So remember, it goes IR, micro, and then radio. Then up here, this is called the UV end. Okay? And beyond the UV are what two? X-rays and gamma rays. They are never present, okay, in a radiation intensity curve. And halfway through next year, you'll learn why that is never present. So this here represents UV mostly. Okay? Now, that means we need to understand what the axes are measuring. What's this bottom axis measuring? Wavelength. Good. And remember, that's always measured in metres of some sort, so it could be nanometres or so on. The vertical axis, did you remember from yesterday what the... Intensity. Right, it's intensity. Now, why am I calling it intensity, not brightness? Right, good. Brightness is associated only with one form of light, which is the visual light. All the others we can't see, so our eye can't determine if it's bright or not. So anyway, this is a way a computer takes a spectrum and is able to work out how much light is present of that spectrum. Is that clear? So in this diagram here, what colour is most present according to my diagram? Cyan. Right, the cyan, the greeny blues and stuff there. Okay? Rightio. Now this would represent, because it's a nice smooth curve, this represents a continuous curve. This is a continuous spectrum. So a continuous curve like that indicates a continuous spectrum. Are we okay with that? Now, when a black line appears on our spectrum, let's say you put a black line there and a black line there, and we have to explain in tomorrow's lesson how these or why these black lines actually occur, but not today. That means that those frequencies, those wavelengths are no longer present, okay, and we're not seeing that part of the rainbow. So what would it do to our continuous spectrum? Right, it spikes down. So at this point here, you would see it go down like that and like that. And that spiking down is seen by our eye as darkness. In reality, it's not all the way down to zero, it's not down to black, but it's down enough that compared to the brightness beside each of them, it looks darker. Okay? Now, it's like saying a sunspot. Does anyone know what sunspot is? These are spots on the surface of the sun caused by massive magnetic field variance. And they are black because they are cold compared to the sun. But when we say cold compared to the sun, they're about 5,000 degrees Kelvin. But the sun's surface temperature is 7,000 degrees Kelvin. So they're very hot, but compared to the sun, surface, they look black. Is that making sense, what I'm saying here? So these here are still quite colourful, but because the surrounding is much brighter, it appears black. And so we perceive these as dark lines. Okay? So are you all answering the question that we're doing as we go? Yeah. Okay, so you know what we're answering at the moment, this question here. It's a matcha thing here. Okay. So that's the two spectrums so far. The hard one to do is the reverse. So I'm going to, I'll just take another slide. It's probably quicker and easier to draw it like that. The last one is an emission spectrum. And what would an emission spectrum look like? Now remember, an emission spectrum is a black background. So let me get the background with that. Let's go away. Okay. And across it, we have some bright lines. So I'm going to put a red line there, a yellow line there, and we'll put a blue line there. Okay? You okay with that? That's what a emission spectrum looks like, also called the bright line spectrum. How would it look like in a radiation intensity curve? Remember, this part is wavelength, and it's measured in some form of meters. Could be nanometers, picometers, or whatever. And this is intensity here. Okay. Right. What this is the reverse of the absorption spectrum. So where the absorption spectrum was a dip in the continuous curve, this is a rise to the continuous curve. So you see that. Okay. Are we okay with that? So an emission spectrum goes up. But the beautiful part is it's got to be somehow related to the continuous spectrum. And the continuous spectrum does magically fit over top of it. So in reality, it's still fitting the continuous spectrum. You just can't see the rest of it. Okay. But obviously, you don't do anything with that red dotted line. Are we okay with that? Now, what causes the three different types of spectrum? Okay, this is the thing we'll be going on to with great detail tomorrow. That one and that. Right, a continuous spectrum is created by any hot object, any solid object which is heated up, or a very pressurized gas which is heated up. So a continuous spectrum is a solid, liquid, or high density gas heated to glowing. Okay? So that's if we just take a piece of metal, like a tungsten filament in our light bulb, we really heat it up, it will start to glow. If you take a solid, like metal, now this is the reason why I put liquid here. The liquid is just the liquid state of the solid. So if you take iron and you heat it up enough, eventually it will melt. And as iron heats up, it will glow red, then goes orange, then yellow, and so on. Eventually, when it gets to really white hot, it will start to then melt upon itself. But the liquid is still white hot. It still glows white. So a continuous spectrum is created by a solid object or a very high density gas heated up so it glows. In other words, our sun is a high density gas ball and it is heated up to glow. So the core of our sun creates a continuous spectrum. Absorption spectrum. This is created, excuse me, my voice is going. The absorption spectrum is created when a continuous spectrum passes through a less dense gas. So a continuous spectrum passes through a low density gas. Okay. This is what we see of the spectrum of the sun, because the outside of our sun is low density gas. That's its atmosphere. But the core of the star, of our sun, produces this, and then the gas of the atmosphere is that, creates an absorption spectrum. Okay. What causes an emission spectrum? This is when you take any gas and you excite it. So this is caused by exciting gas. Okay. Now, how do we excite gas? We can either pass electricity through it, or we could suddenly give it a massive burst of heat. Okay. The other option is emission spectrums are emitted by the gas that creates the absorption spectrum. So they're emitted and I'll explain that more tomorrow. So just so you've got there, let's have a look at the answers to that sheet then. So there is a continuous spectrum, okay, and that's a radiation intensity curve, and this spectrum is created by a hot glowing body which is solid, heated up, or a highly compressed gas when heated up. The next one down is the absorption spectrum. Here is what it looks like photographically. Remember, photographically means what the eye would see. This is what an absorption spectrum would look like as a radiation intensity curve. You can see the peaks going down. And this spectrum is created when a continuous spectrum passes through an uncompressed gas, such as the outer layer of a star. And finally, we have the emission spectrum there. Photographically, the bright lines, this is what it looks like. And the spectrum is created when an uncompressed gas is stimulated by an energy source, most likely electricity. This is how lightning is produced. Lightning is produced as an emission spectrum. And it's also produced when the uncompressed gas that absorbed those wavelengths around the star's core release those wavelengths again into the universe. Okay. Now, I need to talk about, or not just talk about, just mention a few moments what is called a black body radiator. A continuous spectrum is created by a black body radiator. That's a solid object that, when heated, creates a glow. The definition of a black body radiator is that it radiates all heat in all parts of the spectrum when it's heated up. But an ideal black body also is black. That means it absorbs all light that falls upon it. Okay? So a black body radiator is a body that creates a continuous spectrum. An ideal black body also, when cold, appears black. Okay? Now, our sun is a black body radiator. However, our sun can never be cold. But if it was, we could take all the heat out of our sun, it would just appear as a big black ball in space. Okay. It would absorb all light that falls upon it. Okay, it's a perfectly black, that's the reason why black is such a hot colour. It absorbs all incoming radiation. And it perfectly radiates a continuous spectrum. So it's an ideal absorber and radiator of all wavelengths. Now that's an ideal black body. Nothing is ideal. Okay? So most things are approximate to ideal. The incandescent light bulb that we have, the tungsten light bulb, is a black body radiator. But can you actually see the filament? Can you see the filament? If you can see something, that means light must be reflecting off it. If you can see something, then it's not absorbing all the light that is falling upon it. So an ideal black body you would not be able to see excepting for a gap in your vision. An incandescent light globe you can actually see when it's turned off. Therefore, it is not a perfect or an ideal black body radiator, even though it glows very well as a black body radiator as it heats up. Right. All black body radiators go through those colours there. And what do we notice those colours are? Right, that's the colour, not the colour spectrum. This is the glowing colours. And now we can actually call them something. These are called the black body radiator colours, okay? Or just the radiator colours. The radiation colours are those 7. There are other colours in between, but they're the ones that are easily observable. And I'll give you a few minutes to copy them. And these colours are used and have been used now for about 500 or so, even more than that, thousands of years, to determine when iron, bronze, zinc, and all the metals are at a certain temperature for them to be hammered into ploughs, into swords, into spears, and so on. The people who perfected this were the Chinese and the Japanese when they were making these samurai swords, because they knew exactly what shade colour you needed to go to get the hardest sword you possibly can. Because by heating it up, cooling it down, heating it up, folding upon itself, you got really, really good blades. Very, very sharp and tempered blades, they're called. Okay. Now we're going on to a person by the name of Wein. Let's get the right one. And where are you? Plus. Right. A scientist by the name of Wein, or Wien. Now, when he came and emigrated from Germany at the end of the First World War, to America, he had a very thick accent, and on the immigration form, it was written 2 forms of his name. So when you are looking this up on the internet, you might have to search under 2 forms. Now, the syllabus, the New South Wales syllabus, spells his name as W-E-I-N-S, so it's Wein's Law. But the rest of the world have corrected it to Wien's Law, which is actually his name, okay? It's just that when an Austrian says that, it's quite a thick German accent, it sounded like that. So that because of Einstein and all things like that, we're used to seeing that, but not that. Okay. So they're the 2 spellings. Use them either way. I've just kept the one from the syllabus, even though I would prefer to correct it to that one. Okay. So he is a physicist who discovered that you can determine the temperature of an object exactly, not exactly, but approximately, by using its colour. So what he did, he came up with Wein's Law. He observed what we observed yesterday. And yesterday we observed that a radiation intensity curve looks like this. All radiation intensity curves have a long taper down this end. That's a taper. Does anyone know what a taper means? Goes off, getting thinner and thinner. And a massive UV dive straight down on the UV end. But right in the centre, there is a peak. Okay? And this peak, when measured down here, gave you what we call lambda max. Now, lambda max, what's lambda, the symbol for? Wavelength. So this is the maximum wavelength, or what we call the peak. I should call it peak wavelength. That's its proper name. Okay. And he then discovered that just by experimentation, an empirical law, and the empirical law is given to you on this next page over, if you have a look, as T equals W on lambda max. And W stands for Wein's constant, or Wien's constant. And if you have a look on that sheet there, Wein's constant is W equals 2.9 by 10 to the minus 3. Yep. Never remember, I have to look at that one. By the way, this formula is always given if you need to use it. It is not given on the formula sheet, but it is given to you if you need to use it. So, right. So we can work out the temperature of any body simply by using that formula. Okay. Because what do we know happens to that peak as it gets hotter? So going back to what we did yesterday, let's have a look, where is it? Not there, oops, that's it, not there. And, oh, where's the NSJ? Where's my noodle? Okay, just turning that light off for a few seconds. Now, what happens, look at the peak only, the tip. Only this section here. Right, that part there. What happens to it as we heat the object up? So let's heat it up now. Okay. What's it done? Right, so the first thing is it moves to the what direction? Right, now we're going to call it the UVN because the HSE has a tendency to sometimes flip it backward and have the taper down this end. Okay, for some reason it just reverses it all. So it moves towards the UVN, doesn't it? Okay, and what else did it do? It moved up. So Wein noticed that if you were to plot temperature and where it was, there, then there, then there, then there, and so on, this formed a hyperbola. And the hyperbola, he worked out simply the formula of it. So the two things that happen are that a cooler star, here is the star that we're talking about, that's the one that's written in front of you there in question 3. It says below is a radiation curve and its major feature is the tapering long end. You won't see the tapering long end, good. And then a rapid fall at the UV end. Okay? You're asked to, on the grid, draw the graph of, approximately a graph of a hotter star and a cooler star. So let's have a look at, let's draw a cooler star. What would have to happen about the peak, the height of the peak? Right, it's further down, isn't it? What does that indicate? It's not as bright. Remember that the higher the peak, the brighter this object would appear to your eye. Okay. And where's the peak? The peak is to the radio end. Good. Okay. The next one here, I've drawn a blue curve because as in hotter, then hotter objects would appear towards the bluer end of the colour spectrum, of the colour glow spectrum, I should say. And what have I noticed firstly about my peak? The peak is high. What does that indicate about the object that's glowing? It's brighter, much brighter. Good. And what's happened to the actual peak itself? It's also not just moved up, it's moved to the UV end. Okay? In other words, it's getting brighter and giving off more blue and UV light. Okay? Right. Tonight you can have a read of that answer there. It says identify the two changes. The two changes are, it's not just that the curve gets bigger, the curve peak moves to the UV end as it gets hotter. We would do the exact opposite if we got colder. But Wein said, okay, can I work out the exact temperature, when I say the exact temperature, within 10 or so Kelvin, of this curve that I've got here. So let's use Wein's law and read it off. We work out the peak, here's the peak there, and if you read down, you can read off the scale at the bottom what is lambda max. The peak wavelength is 425 nanometers. Are we okay with that? Okay, so let's work out the temperature of the object that is glowing now. Wein's law says the temperature is equal to Wein's constant divided by lambda max. Wein's constant is 2.9 by 10 to the minus 3. And lambda max, now lambda max was 425 nanometers. Okay. So, what is nano again by 10 to the minus? 9. Right, shove that into your calculator. Now, you're not asked to find me on this diagram here. I'm using this as an example. Okay, once you've done this, could you round that number that you've got in front of you to the nearest 10? Okay, because he says it's not that accurate, it's only an empirical law. So what is it approximately, 6,000 or something? 820, and it's Kelvin. I don't care if you put degrees Kelvin, I'm not that pedantic. I know there's a lot of people who say you shouldn't have put the degree sign with a Kelvin. I often say degrees Kelvin, can't be bothered. Are we okay how quickly and easily that is worked out? Okay. Now looking at the next one, this one's for yourself. Okay. Could you now, on that one there, on that A, I think it's 4A, isn't it? Could you read off lambda max, please? 3A. So there is the peak. Now when you are drawing this, you must draw very straight down. Please draw a dotted line directly down with your ruler. See, you are a HSC student now, and the exactitude is getting to the point where you actually have to do this analysis in a HSC situation. Estimate, not estimate as much as you possibly can, as accurately as possible. Write down what you say is lambda max up here, and you can write it down as nanometers. Once you bring that down, apply Wein's law to work out the temperature of that object which is growing. Who's got a value on lambda max, please? Just make sure everyone's working with the same number. 750? Yeah, 750 nanometers. Once you've done that, continue on with the next thing. We're reversing it backward. $3,880. What is it, 3880 is it? 387. Okay. The next one here, you've got to reverse it. You just got to find lambda max. And lambda max would equal W on T. And then you'd have to draw it on here. If it's hotter or cooler, you have to do something.
You always take it to the nearest 10.
It's nearest 10 or sometimes nearest 100, I'll give in the HSC. The machines that are used, say at Fort Kembla, which is like a digital camera gun, digital thermometer like that, they go the nearest degree, they're so accurate. But they use an extended form of this, a corrective form. Sorry? Lambda max should be as near as 5. Okay? Because you couldn't possibly plot it anyway more than near as 5. What does everyone got as lambda max for this one, please? Sorry? 390, sorry. Nanometers. So that's going to be there. Is everyone in agreement that that's 390? Yeah. Okay, can anyone suggest how I would draw this? I know the peak's got to be up here somewhere, but what is it going to look like? Right, it's going to have a higher peak. That's all it's looking for. So you need to have a peak, say, up to here, and it's got to taper down that end, and it's got to dive down that way. Does that make sense how that was done? You shouldn't cross this curve underneath you either. How high is just estimations. It's just got to be high. Did you ask that? Is that you? Or? No, it's just got to be. They're just looking for it to move this way and move up. Yep. Two things that the marking criteria looks at. Okay, now you'll be completing the rest of this sheet for homework, and it's quite quick because once you start doing this, it's just using that law over and over. But it's no use doing these on bodies which are not real. That last one was a nice smooth curve created by a computer generation. Firstly, let's have this is a real star. Okay, I have no idea what the name of this star is or where it is, but what type of curve or spectrum are we looking at here? Sorry? Absorption. What would it look like photographically? Or, sorry? What would you see? Yeah.
The black line.
Yes, you see black lines. So you see a continuous spectrum with black lines. Okay? Right here. And where would be the darkest, thickest black line, do you reckon? Here, can you see it? That would be quite a thick. These would be all little small black lines. Right. Now, to use Wein's law, we need a continuous spectrum. So what you're going to do is you just simply make it a continuous spectrum. Can you see how doing that, you've got to actually be a bit more exacting than me. Let's see, just join the peaks and down. Is that better? Can you now read off a lambda max? Can you read off a peak wavelength now? Would a peak wavelength be there if you use a ruler? Good. Okay, off you go. Work out the surface temperature of that star. And then move on to the next part of the things.